Imagine you have a sensitive electronic device, perhaps a complex microcontroller, a precision sensor, or an audio amplifier. If the power supply to that device isn't perfectly steady, what happens? Your device might malfunction, produce inaccurate results, become unstable, or even suffer permanent damage. This instability is a common challenge in electronic design. This is where voltage regulators become absolutely essential. They are critical components in direct current, or DC, power supplies, specifically designed to maintain a constant, stable output voltage, irrespective of variations in the input voltage or changes in the amount of current drawn by the connected load. Their primary role is to ensure a reliable and clean power source for delicate circuits. The raw direct current generated by a typical power supply, even after it passes through a rectifier and an initial filter, is rarely perfectly smooth. It often contains undesirable variations such as ripple, which are small alternating current components superimposed on the direct current voltage. Furthermore, the voltage can fluctuate due to changes in the alternating current power delivered from the electrical grid, or because the amount of current demanded by the electronic circuit, known as the load, changes. Without effective voltage regulation, these instabilities would directly impact the performance, accuracy, and overall reliability of sensitive electronic components. Voltage regulators work by continuously monitoring their output voltage. If the output voltage starts to deviate from its target, they dynamically adjust an internal series resistance or control their switching activity to bring the voltage back to the desired precise level. This process effectively isolates the sensitive load from upstream disturbances and downstream load variations. In the architecture of a standard DC power supply, the voltage regulator is strategically positioned after the rectifier and the bulk filter capacitor. The somewhat smoothed, but still unregulated, direct current output from the filter stage serves as the input to the regulator. The regulator then meticulously processes this input, often stepping down the voltage and performing a much finer level of filtering to deliver a highly precise and unwavering direct current voltage to the downstream electronic circuits. For a practical example, consider a microcontroller operating at 5 volts. You might have a 12-volt direct current supply from a wall adapter. A voltage regulator would efficiently convert that 12-volt input into a stable 5-volt output, crucial for the microcontroller's reliable operation. Engineers typically choose between two main types: linear regulators like the familiar 7800 series, which are simple but dissipate excess voltage as heat, or more energy-efficient switching regulators, which are ideal for higher power applications and when heat generation is a concern. To truly appreciate the effectiveness of a voltage regulator, we evaluate its performance using key specifications. Line regulation quantifies how consistently the output voltage stays at its target value despite changes in the input voltage. For instance, if the incoming alternating current mains voltage fluctuates, a good line regulator will ensure the output remains constant. Conversely, load regulation describes the regulator's ability to maintain a steady output voltage even as the current drawn by the connected circuit varies significantly, perhaps from a low standby current to a peak operational current. Both line and load regulation are often expressed as a percentage, with lower percentages indicating superior voltage stability. While simple Zener diode circuits can offer basic voltage regulation for very low power applications, modern integrated circuit voltage regulators provide for more sophisticated control, precision, and protection features, making them invaluable in virtually all contemporary electronic designs. Ultimately, voltage regulators act as the silent guardians of stability within our electronic ecosystems. By meticulously transforming potentially unstable and noisy direct current power into a clean, consistent, and predictable voltage source, they are instrumental in extending the lifespan of components, ensuring the accurate execution of complex operations, and maintaining the dependable performance of everything from the simplest battery-powered gadgets to the most intricate computing systems. They are truly indispensable elements, safeguarding the integrity of electronic circuits worldwide.